All right. Told you what we were doing. Review quiz. Both these 2 days. You got a 4-day weekend ahead of you. And then Maroon 1, Maroon 2, lunch, Maroon 3, go away. Go away. White 1, lunch, White 2, go away. White 3, White 4, lunch, go away. Is the jam. So technically, you crew have to be here these 2 days. And let's be perfectly honest, if I then give you a quiz over a week later, probably ain't going to go so hot, is it? Kind of like when y'all voted to have a quiz the day after coming back from break. So, the plan is, in front of you, you have half of a review over the semester. You will take a quiz over half of the stuff in the semester. And that's it. That's what we do today. We do it again on Thursday. And then assuming that you have everything done, that you have all of your quizzes in, that you are doing all of your work, then as far as I'm concerned, you're done. You don't need to show up on that Friday. If that's the case. You do have until that Friday, that block, that scheduled time for this class to get the last year stuff turned in. Most of you are doing good. Some of you on a border. It depends, well, basically it just depends whether you've been given a rip or not. So, let's hop to it, because this should all be old business. Do you all have quizzes 1 through 5 in front of you? Review and quiz 1 through 5 that you have already taken, that I handed back to everyone. Maybe if you turned yours in late, I might have a few. But I thought I turned back most of yours. No, that's first block, first block. First block, first block, first block. Dang. I might just not have handed back 5 to first block. Oh no, they're just slow. Oh, I got 1. Here you go, Trey. So if in the past week you've turned in stuff for me, that's my plan, is to go through that, well, while you guys are doing these. Okay? And we'll be all squared away. And you should know, I'd say by Tuesday next week, you should know in the next week exactly where you sit. Like final grade. So, review. All right, we're going to start off with properties. There's a bunch of them. If you got your old packets, chapter 1, sections 1 and 2. Which means this would be a great time to write something down, because you get to tell yourself how to do it. If you decide that I'm just not going to do it, then I'm not going to have any sympathy if it doesn't work out. Okay. Bud, you're right there. You're right on the border. You got this as long as you just do it. It sucked to give up a whole year because we decided not to do it at the last minute. That's like running a marathon. You turn the corner 3 blocks down there, you can see the finish line, you're like, nah, I'm good. Okay? We're right there. We're almost there. Properties we had were things like A plus B equals B plus A. This is also true for multiplication. What was that thing called? Ooh. How about this? One of these is associative. One of these is commutative. Okay. The way that I think of... All right. I always remember associative because it's got some associative cheeks on it. It's got butt cheeks on it. It's associative. Okay? This one says order doesn't matter. Associative says grouping doesn't matter. Guilty by association might be something you've heard before. After all, you are teenagers. We also had other ones like the identity properties that said, what do I add to A to make it still A? 0. Or what do I multiply A by to still make it A? Those are the identity properties. There was the special multiply by 0 property that says anything multiplied by 0 is still 0. There's the distributive property, which combines multiplication with addition. And there's some other stuff. I'm probably forgetting something, but those were the bulk of it. So when they ask us to say which property this is, you look at the first one, and the first thing you should ask yourself is, it's got parentheses in it. What 2 things have parentheses? Associative and distributive. Ask yourself, did the order change? 3, 6, A. 3, 6, A. The order is the same, but the grouping changed. Grouping doesn't matter. So that's your answer. This is the associative property, and specifically tell me of multiplication. Because remember, associative of multiplication and associative of addition are different. They do the same thing, but one is meant for multiplication, the other is meant for addition. What about 2? I took 2b and I added absolutely nothing to it. So now it's still 2b. That would be the identity property. And specifically, it's the identity property of addition. Okay, exponents. We spent a lot of time on exponents. And we reviewed them an awful lot. Exponents kept popping up on all of our quizzes. So let's write some properties here. If I took x to the a times x to the b, what do you do when you multiply exponents? You add them. How about if I divide exponents? Oh, you subtract. Everything gets downshifted in one operation. What if I have an exponent raised to an exponent? We already took care of the add part up here. We multiply them. A times b. What if I got more than one thing in there? What if it's like x to the a, y to the b, both to the c? Everyone gets that exponent. Yep. This also works for if it's a fraction. X to the AC, y to the BC. What if I have x to the negative a? Kick it downstairs. Remember that light switch? If it's a negative upstairs, throw it downstairs. If it's a negative downstairs, throw it upstairs. So likewise, if I had 1 over x to the negative a, that'd be x to the positive a upstairs. And then everyone's favorite rule, anything to the 0 power. Womp, womp, womp. One. Okay, a little bit of review for you. What if I say 5 over 5? 5 divided by 5 is 1, right? I got 5 things. How many ways can I put 5 things into a box? But what if that is instead x to the 5th over x to the 5th? We agree that this is 1, right? But then we also say that's x to the 5 minus 5, which is x to the 0. That's why anything to the 0 power equals 1. Okay. So I'm going to leave all these blue properties in the middle here. First thing, do I got any exponents outside the parentheses that I have to take care of? No. So now you just multiply stuff together with the multiplication rule. I'll multiply the 4 and the 3 together, the x and the x cubed together, the y cubed and the y to the 5th together. And I say 4 by 3, it's 12. That's regular. Those aren't exponents. You remember what little invisible exponent's up here? So 1 plus 3 is x to the 4th. 3 plus 5 is y to the 8th. Might want to make a big, giant, neon, holy crap warning sign to yourself. I saw kids doing this. You can't do that. Like this literally says 12 times 1, 2, 3, 4 x's. 1, 2, 3, 4, 5, 6, 7, 8 y's. I can't say that there's 12 y's and 1 x. These are not the same base, so I can't combine their exponents. Like trying to mate a turtle and a giraffe. Fun to watch, it's not going to accomplish anything. Okay? So just leave it like that. You got your review right there, bud. Contestant 2, do I have exponent outside that needs to be taken care of? So we get to be mathematical Oprah. You get a 3, and you get a 3, and you get a 3. Invisible 1 there. And whenever I take an exponent to an exponent, we multiply them. So that's an x to the 4 by 3, y to the 2 by 3. So that's 5 to the 3rd, x to the 12th, y to the 6th. I ain't done yet. The 5 to the 3rd is an actual number. I can find it. Either I know where the exponent button is on my calculator. It'll look like this. Maybe this. Maybe a combination. Maybe you'll have to use the caret button. Depends on the model of calculator you're working with. Or you can just take 5 times 5 times 5. Don't take 5 times 3. Don't you dare say 15. How about we mental math this because we know money? What's 5 times 5? 25. What is 5 quarters? I hand you 5 quarters. It's $1.25. This is 125. Okay. First things first. Only to the ones they're touching. Yes. You get a 3, and you get a 3. You get a 5. Then clean it up. 2 times 2. Times another 2. 8, not 6. Use the calculator to double check it if you're not sure. You know what? Even if you think you're sure, still double check it. Free points, right? A to the 3rd, B to the what? 20. Who gets that negative 4? Everybody. So 3 gets a negative 4, x gets a negative 4, 2 gets a negative 4, z gets a negative 4. Oh no, they're all negative. I'm going to do this 2 different ways. Now, see how they're all negative? Flop all of them because they're all negative. I have to flip all those light switches. Have you ever been that kid where you see that bank of light switches? There's like 4 or 5 of them on the wall. You walk over, you're just like, still do. Okay, so now that's 2 to the 4th upstairs, z to the 4th upstairs, 3 to the 4th upstairs, or downstairs, x to the 4th downstairs. To which I say, what is 2 to the 4th? You sure? Okay. 16. 3 to the 4th. 3 by 3 by 3 by 3. 81. 81. You know you can do it in stages too, because grouping doesn't matter. You say 3 by 3 by 3 by 3. 3 times 3 is 9. 3 times 3 is 9. 9 times 9 is 81. Now, Nevaeh's over there getting kind of a scrunched eyebrow about why we went here. See how the whole thing was negative? I could have just table flipped the whole thing at the beginning. Then give everyone the 4. Because it's still going to end up in the same spot. You'll see that with these problems because exponents are repeated multiplication, and multiplication is commutative, so the order doesn't matter. The order in which you do these, as long as you're following math law, will not matter. There might be 9 different ways to do a problem. There might be 30 ways to do a problem. Ew. Take them one piece at a time. Look at your number stuff. I can reduce the number stuff. What have 15 and 35 got in common? Okay, so if I say this divided by 5 and this divided by 5, then I have reduced said fraction. You could also just grab a calculator, scientific, I made sure you all had one, and type in 15 over 35, enter, and it'll reduce it for you. So I got a 3 up top, I got a 7 downstairs. I'm going to put the negative out front. Remember that the negative can go here or here. Even though technically it can do this, that's considered very improper. That'd be like wearing your underwear on the outside. You can do it. Superman been telling people to do that for decades. You can do it, but people are going to look at you funny. Especially if you got racing stripes. I mean, just saying. Okay, nope. Oh, all right, I'm going to say it anyway. One of my buddies in high school, in the middle of a football game, like senior year, everything on the line. When you go hard. He crapped himself in the middle of a game. He hit a guy so hard that he crapped his own shorts. Oh, man. His name's Aaron Nash, by the way. Look him up, mock him on social media. Super nice guy, but... All right. What do I do with an exponent over an exponent? Okay. So 3 minus 4 is a negative 1. I'll take care of that later. Chill. B stuff. Negative 2 minus 7. Or negative 2 minus 5 is a negative 7. Spoiler alert. And then because I have 2 negative things, so it's a negative 3 over 7a to the first. I don't need the 1 now. B to the 7th. Now another way to do this, do you remember the who's got more game? Look at your A's. Who's got more? The bottom does. By how much? 1. So put an A to the first on the bottom. Negative 2 and 5. Who's bigger? By how much? No. From negative 2 all the way to 5. 7 bigger. What you're doing is subtracting. You are subtracting mental math style. It's just another way to think of it. You can do it if you want to. You don't have to. Anything, I don't care how big it is. I could fill this entire board with an expression, a formula, full of symbols you don't even know exist yet. The entire board, just nasty math everywhere. As soon as you throw a set of parentheses to the 0 on there, 1. Okay. Solve, or does everyone have their perfect square list? Section 1.4. So if you have your chapter 1 packet, some of you wrote it on a note card to have somewhere else. If we do not have it, maybe we should write that down super quick. 1, 2, 3, 4, 5. Man. Is 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, I always stumble on that one, 225, 256, 289, 324, 361, and 4 hondo. You should have your perfect squares through 20, if not memorized, written down and easy access. Those are your prime numbers. When we look to do prime factorization later when we're simplifying these. We're going to get to that in a minute. So I'm going to do these out of order. I'm actually going to start with B, then C, then A, for reasons. Is 361 on that perfect square list? Yes. Yeah. What's the square root of 361? So I can take a 19 out of this. Remember that this says 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 A's. 1, 2, 3, 4, 5, 6, 7, 8 B's, a 19, and a 19. What I'm really doing here is saying there's a pair of 19s, one of them gets out. Every time there's a pair of A's, one of them gets out. Well, that's going to happen 1, 2, 3, 4, 5 times. And A to the 5th is going to come out. Do you remember the trick? Okay, level 2 guard. He says, no one's getting past me. Then 2 guys bum rush him. One of them gets out. Okay? You're looking for pairs. Because this divided by 2, half of them will tackle the guard, half of them will get out. A to the 5th. B to the 8th. Just divide it by 2. Just circle. There's 1, 2, 3, 4 pairs. 4 of them are getting out. See how everything inside was crossed out? No one's left in radical jail. There's a 19, A to the 5th, B to the 4th on the outside. Look at C. The square root of 9. The square root of W to the 18th is W to the 9th. But there's already a 13 out there. That's their buddy who was waiting for him to get out of radical jail. That's the getaway car. Okay? So they're all going to jam together. You say 3 times 13 is 39, w to the 9th. If there's already something outside of the radical, whatever comes out just joins it. So the reason I did those two first, square root of 25 is 5. But I can't exactly cut x to the 7th in half. And that's how we dealt with it. We said, since that thing's problematic, let's do this. Let's put one of those x's over here. See how it's still x to the 7th? There's still 7 of them there. We just divided its attention a little bit. And now, square root of 25 is 5. Square root of x to the 6th is x to the 3rd. But he's still left in radical jail. He didn't have any friends. He didn't have anyone to buddy up with. So he stays in there. So that's my answer. A 5x to the 3rd outside is still a square root of x inside. Cool? I'm going to leave this perfect square list here. It's going to come in handy. Is 196 on my perfect square list? And since there's a negative right here, it joins it. Is 48 on my perfect square list? No. Now, when we first learned how to do these, I said, you know, that's awful close to 7. Right? Because it's in between 49 and 36. So its answer will be between 6 and 7. But it's closer to 7 because that's closer to 49. That was the first way we learned it. And then I showed you the true ways of the force. That I can change this number and reduce it. $48. There's 49. Okay. Starting here. Does 48 divided by 36 happen evenly? Nope. What about 25? 16. Oh. So since that's 16 times 3, I'm just going to take that part of it out. Square root of 16 is 4. So the 4 comes out of radical jail and the 3 stays in. Just like with those x's. Now if you get stuck, there's a way to get unstuck that says prime factorization. What's anything times anything that you already know makes 48? Don't choose 16 and 3, that's what's right there. You're like, 6 times 8. Okay, that works. What times what makes 6? What times what makes 8? Can I break up 2? 3? 4? 2? 2? 2? No. This is what the prime factors were for. Prime factors are numbers that can't be broken down anymore. So you look at the ends of your branches and say, I'm going to rewrite this as 2 by 2 by 2 by 2 by 3. And then I look for pairs. A pair of 2's, 1 gets out. A pair of 2's, 1 gets out. But you notice it's the same thing. You try. Except whatever comes out joins the 3. That was quick. Which of those perfect square numbers goes into 75? So I turn it into 25 by 3. And I say the square root of 25 is 5. 5 joins the 3. 15 square root of 3. Cool so far? I'm actually going to start over here. Domain. Now we're at section like 1.5 through 1.7. Domain is the what? X's. Also called the inputs. Range. Also called the output. So if I want to list the domain and the range, I literally just write down numbers. Yay. What do I not want to do, though? Okay, that's when we're looking for functions. That's coming up. Okay, that is coming up. I don't want to rewrite them. If anything ever happens more than once, don't write it more than once. I know, that's why I pointed at you, because you said it. You were right. Yay. Back there getting all teenage girl hostile on me. Because you said it. So I said it louder for everyone else. Maybe other people just tune you out. Dance, puppets, dance. Okay, I'm just writing them down. That's it. These ones, I'm going to write them in numerical order. Oh, that's positive 1. I don't have to. It just helps. Okay, so negative 3, but negative 2 happens twice. I don't write it twice, I just write it. 1 happens twice. I'm just going to write it. And then 6. That's it, domain and range. Just write the numbers. Do you remember how to do that when it's graphed? Ooh, okay. We're starting to confuse how to write it with how to look for if it's a function. That's coming up. Now, sometimes we want to just write out the coordinates because maybe it's hard to see what the numbers are without writing the coordinates. So maybe I would write, how do coordinates work again? It's always an X, then a Y. And if we need to write this, to remind ourselves what it does. So from the origin right here, B goes back 4, down 3. Negative 4, negative 3. A goes left 3, no up or down. Negative 3, 0. C goes no left or right, but up 2. So 0, 2. And D goes right 1, down 2. So positive 1, negative 2. Okay, that makes life easier now, right? If you want to put them in a table first, in fact, you can say your domain and range as a table, like this. I say my x's. We got negative 4, negative 3, a 0, and a 1. The y's. I got a negative 3, negative 2, a 0, and a 2. You could write it like that. I don't care. It's all good. You know what? I would actually say make sure that you put domain and range so we understand. Now, you don't have to write out the coordinates either. You could use a pencil, a ruler, something tracking across the page. You say, shoop, found one. This is the x-axis, so that's at negative 4. Found one. It's at negative 3. Found one. It's at 0. Found one. It's at 1. You could do it like that. Flip it on its side. Do the same thing for y's. And say, found one, negative 3. Found one, negative 2. 0, 2. As you move your way up. So you don't have to write the coordinates out if you don't want to. It's just a way that might help you. Now, some of you were looking at jumping into the next thing, which says, is it a function or not? First, do we remember mappings? Okay. Perform your tasks, little space soldier. The domain, all of the x's. So negative 11, negative 6, negative 3, 0, 1. All of the y's. And we say 8, 11, 21. And then cross your wires. Say negative 11 goes to 21. Negative 6 also goes to 21. Negative 3 goes to 11. 0 goes to 21. 1 goes to 8. Man, that's an argument over there. That was some definite, if you want to cry, I'll give you something to cry about mama bear energy right there. Okay, the argument is, are they allowed to all go to the same 21 and still be a function? Each of the x's, think of it as a button on a machine. I pressed the negative 11, it did a thing. I pressed the negative 6, it did a thing. Did I ever press a button more than once? No. And if I did, it would still be a function if it went to the same place. This would be the pop machine that has 3 Mountain Dew buttons on it, a Pepsi and a root beer. As long as each of these does what it's supposed to do, it's fine. It's when I press that button again and it goes and gives me the root beer, well, now we got a problem. Yay or nay? Hmm. I press the 1 button. Does it only do one thing? I press the -3 button. Does it only do one thing? I press the 8. I press the -8. I press the 20. I never actually pressed a number more than once. So yes, this is a function. And if I'm going to explain that, I'll say yes, function. Now technically what we're supposed to write is every element of the domain maps to exactly one element of the range. What I write is every x goes to 1 y. Good enough. If every x or every part of the domain, because the x's are the elements of the domain, the y's are the element of the range. The further you go in math, you start doing lots and lots of proofs where you have to show conclusively, logically, without fail, this will always happen. And we start making up a lot of symbols because otherwise every one of these proofs would look like a dissertation. All right, bonus round. Is it a function and why?
No, because 20 goes to 2 different.
What about the -3?
20, or not, the -3. Yes, because you can push the -3 twice, it gives you the same number.
Exactly, that button's doing what it's supposed to do. But yep, I press the button. My radio's volume goes up. I press the button again and it honks at the person in front of me. Okay? I press the button, my garage door goes up. I press the button again and a spring trap pops out of the middle of my yard. Line test. The vertical line test is a way of saying this button is 1, 2, 3, 4. This is x equals -4. If I press the -4 button, I'm going to look for what y it gives me. And it only gives me 1 y. I press the -3 button only once. -2, -1. 1, 2, 3, 4. Every time I press the button, every time I looked at one of those x equals a number vertical lines, it only hit it once. What about now? What about now? Okay. So my answer is going to be yes, because it passes the vertical line test. Okay. That works. And finally, for our first half review, graphing by tables. Do y'all remember there was a trick to these? What? The denominator of this means that I'm going to have fractions everywhere. Don't write this part. If I put -5, -4, -3, -2, -1, 0, 1, 2, 3, 4. If I put in a -5, I got -5/4 minus 1 is -9/4. Put in a -4, I'm going to get -2. Put in -3, I'm going to get -3/4 minus 1 is -7/4, is -6/4, which reduces. Is -5/4. Is -4/4 or -1. Is -3/4. -2/4, reduce it. -1/4. And then 0. Out of all of those, you notice the ones that actually ended up nice were the ones that were divisible by 4. So that's the trick to these. You pick numbers that are divisible by that denominator. I'm going to choose -8, -4, 0, 4, 8. I'm also going to be able to see a pattern pretty quick. So it's -8 divided by 4. Close. -2. And -2 minus 1 is -3. Stick a -4 in there. No, we have challenged the ruling on the field.
Okay.
You owe me $2, you borrow another one. Yep. And sometimes, given my mental state in the last year, I check my work a lot more nowadays because it just doesn't sound right. I stick in a 4. -4 divided by 4 is -1. -1 minus another 1, -2. You owe me $1, I let you borrow another $1, right? If I stick a 0 in there, 0/4 is 0. 0 minus 1 is -1. You see the pattern? What's it doing every time? Okay, -3 and -2 and -1, 0, 1, 2, 3, 4, and so on and so on and so on. And now I go and plot my points. This says back 8, down 3. This says back 4, down 2. No left or right, down 1. Right 4, no up or down. Right 8, up 1. Oh, yes, you do. Don't make these lines ugly. Have some respect, child. At the very least, you should have your school ID on you. If you have any of your old reviews and quizzes, I strongly recommend that you have them on hand for this because it's just more stuff to help you through. You have about 35 minutes in class to do the thing that we just did. And I'm actually short 1. Did I give you one the other day? I thought I gave you one.
If we don't finish this in class, then we'll,
Just like any other quiz, finish it, turn it in. Review final. You need another one? Okay. Oh, there's one. I knew I printed enough off.
Thank you, sir.
Uh-huh. Just like any other quiz, don't freak out about it. Let's just take a quiz. So, take your time with it, jam if you need to jam. And that's all we do. You come back on Thursday, we'll do it again.